Okay, hello everyone. Welcome to the fifth lecture in machine learning. Okay, so maybe let's directly jump into the lecture today. Let me share my screen. Okay, so let's actually start with a quick review of like what we have learned from the previous lecture. Um, oh, I remembered that I should do a quick announcement. Now I remember. Okay, so let's go back to the slides and work. Okay, can you see the slides? Okay, so a couple of quick notes. So the lecture videos are all available in the, like initially I was trying to put the lecture videos and scribbles in every lecture, and it's a bit painful process for me to add links to every row in the table. So as a lazy solution, like, so what I have done is like I have given you the link to the entire YouTube playlist in the top of the schedule. Similarly, like there is a link to the Google Drive, which has all the scribbles. So every time like a lecture is over, I'll just put the scribble there. It's a much easier process for me to do than like finding a link to share and then adding it to this row. So these are the two things I just, okay, someone says there's no voice. Okay. Uh, okay, so yeah, so these are the two links I just wanted to mention. And also, I'm not sure if you guys are regularly following the reading materials. So the reading for this week was already posted, which was the linear algebra review and the review about Lagrange multipliers. For the next week, the reading is a bit of intro to convex optimization, like which is also already available now, like in case you finish reading for this week. As you might have noticed, like the readings are complementary to whatever we learn in the class. Sometimes these readings are required for you to understand the future lectures. So I recommend you to take these readings seriously and like do them every week. And the reference for all the chapters or the lectures have been updated here. I had a couple of feedback from the anonymous Google form. So one is the audio quality was very bad. I'm sorry, like I was using my earphones and I was not watching the YouTube video, so I was not sure what is the quality of the audio was, but I just switched to an external microphone. So I'm just curious to know if this is better than the previous lecture. So let's do a quick poll. Press A if you think this audio is better, B if it's not good. A if the audio is better than the previous, B if it is not. Please don't do C. Okay, so there seems to be a clear message. This is better. I'm happy. Well, I wish the person who gave that feedback gave it on the first lecture so that like I could have bought this microphone sooner. But still, like I think future lectures will be better in terms of audio quality. And there was also another comment that the notes are a bit too rough in the sense it's not very detailed. It's just to the point, more like slides. Well, like, so this is the first edition of this course, and hopefully in the future, like I will elaborate the notes more, but I'm trying to strike a balance between having like a really verbose notes versus like something which is to the point and helps you to quickly review what has been taught in the class. So in some sense, the notes are not meant for like just self-reading. Like, so you should also attend the lecture so that like you get the context. But hopefully in the future, like I will like make it even more elaborate, but definitely not for this edition. So, but maybe one thing that I could do is like for the future notes, like I will try to make sure that like it is as elaborate as possible, like even like within the minimalistic setting. And there were also a lot of positive feedback. So thank you all for both the positive and negative feedbacks. So, okay, so for the self-assessment, yes, I should update the self-assessment with other chapters. I will do it soon. Okay, so those are little informations, and let's get into the lecture. Okay, so let's start with a quick review of like what we did in the previous lecture. So we started discussing about two different algorithms that we have learned in this course, which is least squares and nearest neighbors. And we discussed the differences between them, which led us to the question of, given a prediction problem, like whether it is regression or classification, what is the optimal function to solve this problem that solves this problem, right? Like, so, and we tried to answer this in a very abstract sense. And what we found is for regression, the conditional mean is the optimal thing to do if you are measuring your error by squared error, right? Like similarly, and we discussed about how nearest neighbor is trying to approximate this conditional mean, and also how linear regression or least squares is trying to approximate this conditional mean. And then we also discussed similar things for classification, like where we found that the best thing to do is to predict the most probable class, where the most probable is defined based on the true joint distribution, probability of g comma x, which we will almost never have access to for any of the real life problems. And the classifier, which the optimal classifier which makes this prediction, is known as Bayes classifier. And we also discussed that the Bayes error rate, which is the error by this classifier, is something irreducible, because like we can never like do better than the Bayes error rate, simply because this is the lowest possible error that you could achieve, given that the process itself is stochastic. So then we switched to regression. Like we started looking at basis function based regression models, where the idea is like instead of making your model nonlinear with respect to the weights, which will make the optimization problem harder, we made the model nonlinear with respect to the input. We took the x and we added a fixed nonlinear basis function to the x, so that we can actually model complex decision boundaries, right? So, and we discussed about different types of basis functions. Like, to give some example, I'm just trying to find where the example is. Well, I don't see the example. Wow. Okay, I don't see the example. But we did have some visualizations for sigmoidal basis functions, or Gaussian basis functions or polynomial basis functions. Okay, I'm just trying to find where I missed it. Okay, I'm not sure. Okay, and then we looked at the geometry of least squares. We also discussed how to do linear regression when you have multiple outputs, right? So that is where we stopped. Now let's move to today's lecture. Okay, so as a reminder, when you have questions, like I will tell you when I will take questions, and you can ask your questions. You can also post your questions in the chat, and Remy would ask me them like during the question time. Okay, so let us begin. So in this lecture, we are going to look at a new learning algorithm, which is gradient descent. Okay, so let's see how to do learning by gradient descent. Okay, so to do this, we are going to consider the simple regression problem that we have been using as a running example in this course, which is the housing price prediction problem. Okay, so in this case, X is a single feature, so x belongs to R, and y, the target, is also a single variable, so let's say y belongs to R. The linear regression model that we have seen so far is given by y hat of x given w is equal to w0 plus w1 x, right? Now, what are the parameters of this model? The parameters of this model are w0 and w1, right? So, and we also have a loss function, which is the MSE. The loss function is given by 1 over 2n summation over I is equal to 1 to n y hat of xi given w minus yi, the whole square, right? So in this case, y hat is model's prediction and yi is the true target that we want to predict. Okay, so now once you define the loss function, you have a goal or objective, and our objective is to minimize the loss function. So find the parameters w0, w1, which minimizes this loss function, right? So in this situation, like when we have a linear regression with least square error function, okay, so there is a question which is this a cost function or a loss function? They are both same. Sometimes you call it as a cost function. Sometimes you call it as a loss function. So you just different, like you're minimizing, like both means that you're minimizing something. You're minimizing the cost or you're minimizing the loss. Okay, so we are interested in minimizing this loss function, right? And in this case, it happens that it's a like easy problem to solve, like when you have a linear model with like a least square objective. And in fact, we were able to solve it analytically. We have derived this solution previously, which is your W star is given by X transpose X inverse X transpose Y, right? So we did derive this solution directly. And in this case, like when you do this in your assignment, like you would directly implement this equation to find W, okay? So this is basically the analytical solution for this problem, okay? However, in the future, like we are going to look at complex problems where coming up with an analytical solution is not possible. So there are situations where coming up with analytical solution is not always possible. Okay, so now we need an alternate way of finding this W star, right? So if I cannot come up with this solution in like an analytical form, like how do I find this solution? So now this is when we can use gradient descent to understand gradient descent. So the first thing that we are going to do is to look at the loss surface for our loss function. So in this case, this is a 3D plot where you have W0 and W1 in two axes. The third axis is basically your loss function. Okay. Now for every possible value of W0 and W1, I'm going to compute the loss in the training data. And I just plot this for every possible W0, W1. And now this specific plot is the loss surface for our loss function. Okay. Now, like any specific part, for example, if I take this specific point that belongs to a specific configuration of W0 and W1. Okay. Now, what do we see from this loss function? So the main, like one thing that we quickly notice here is this loss function seems to be a very smooth function. Like the surface seems to be very smooth, that there is only one minimum point, right? So there is only one minima for this function. Okay. Now, given that this is the loss surface for linear regression, can anyone come up with an algorithm to find this minimum? No chat, use raise hand. I want a specific answer. Masood, Remy, can you unmute Masood?
Okay, just calculating the derivative of the function and I mean, just let it equal to 0 and find the, but the function is multi-dimensional.
Okay, can you repeat your answer, please?
I mean, find the derivative of the function equal to 0.
Okay. Okay, so like you do that for the analytical solution, right? Like you differentiate, set it to 0, and you find the analytical solution. Let's say you cannot find that analytical solution. In that case, how would you solve this problem?
Oh, you mean the function is not derivative?
No, you could derive. Okay, no, you could compute derivatives for the function. It is just that you cannot compute the analytical solution for the derivative equal to 0.
Okay, maybe Newton method.
Sorry, what?
Newton method.
Okay.
I don't know.
Okay. Bruno.
Just Newton.
Okay. Okay.
Newton method.
Okay.
Well, we can calculate the derivative at that point, or rather the gradient, and it's going to point like up, and we want to go the opposite direction.
Okay.
And we take steps until we reach a point where the derivative is 0.
Okay.
And we find the local minimum.
Okay. So that is, thank you. So that is exactly what gradient descent is going to do. So even before understanding about derivatives and going in the opposite direction of derivatives, let's just look at this picture, right? So now let's say I choose a random W0, W1, and let this black dot be the loss that I receive. Okay. So imagine I put you blindfolded in the place of this black dot. Okay. Now I want you to go to the minimum. So how would you go to the minimum? Like when you are blindfolded, so you are going to check with your legs, like which is the steep which is going down, right? So there are like many possible ways in which you could go, right? And possibly this red color circle thing is the one which goes down. So you'll take that step and you slowly go down, go down, go down, right? Like so you would be taking small steps, and you will reach a point. So you will stop where you cannot take any more steps which goes down. So once you are in the minima, all the steps are going to take you high, right? So now this is exactly what gradient descent is going to do. Now, how do I find which is the steepest descent direction that I should take? So that is given by your derivatives. So at any point in your loss function, if you take the derivative is going to tell you the opposite of like your descent. And like you would basically do a negative of that to get the grade, like to get the step. Okay, so now let's look at the outline of how gradient descent is going to look like. So basically we will start with some W0 and W1. Okay, then you keep changing W0 and W1 to reduce the loss W0, W1 until we hopefully end at the minimum. At the minimum. Okay, so now the mathematical way of saying the same thing is by this simple algorithm where you basically repeat until convergence. Okay, the weight parameter Wj is equal to Wj minus some alpha times dou by dou wj of the loss for both j is equal to 0 and j is equal to 1 simultaneously, for both j is equal to 0 and j is equal to 1. So what do we do here? So we first compute the gradient of the loss with respect to the parameter. Okay. Now, and you do a minus so that you're going in the descent direction. You don't want to take a big step. So you're going to control your step by alpha, which is the step size or learning rate. Okay. So typically you have an alpha like 0.1 or 0.01 or 0.001, and you take tiny steps and slowly go towards the minimum. Okay, is that clear? So in this picture, for example, if you randomly start here, you take one step of gradient descent, like, and depending on your learning rate, like, so the gradient tells you the direction and the learning rate or step size controls how far you're going in that direction. If your learning rate is small, you would do a small step like this. If your learning rate is large, you would do a big step like this. And you would keep on moving until you reach the minimum. Okay, so now a couple of comments.
Just before, we had a question from Yumla.
Yeah.
Yes, my question is that this method is going to allow us to find the closest minima to the point, the starting point, right? So
Yes.
not the minima of the entire loss function, right? Not the global minimum.
Yes, we will come to that very soon.
Okay.
But remember that in this case, for linear regression with least squares, there's only one minima, right?
Yes.
So
yes.
the loss function shows there is only one minima. So we don't have that issue yet. So we will come to that issue very soon.
Okay.
Okay, a couple of note. So first of all, if your alpha is too small, then your steps are going to be tiny. So your gradient descent is going to be very slow. So let's just call gradient descent as GD. So gradient descent can be slow. Okay. Then the second note is if alpha is too large, okay, in that case, the gradient descent can actually overshoot the minimum. For example, let's take the 1D case. So now this is my loss function. Okay, this is just a one-dimensional loss function, and I have my minima here, right? So let us say I am already here. Now I need to take a very small step, another small step to reach here, right? Now, instead of taking a small step, let's say I have a bigger learning rate. In that case, there's a chance that I could overshoot this minima. And even worse, with a big learning rate, you could even diverge. And like and basically blow up your parameters. Okay, so basically, if alpha is too large, you can overshoot the minimum, or you may even fail to converge and even diverge. Okay, another interesting note is, so this problem doesn't mean that as you go closer to the minima, you need to change your learning rate, okay? In fact, even with a fixed learning rate, the gradient itself is going to shrink as you are closer to the minima. So that will take care of the learning step. So basically, gradient descent can converge to a local minimum even with the learning rate alpha fixed. So as you approach the minimum, the gradient itself is going to shrink. So it will take care of convergence. So you don't need to reduce your learning rate, like depending on the time. Okay, so now let us see how to do linear regression, like how to do gradient descent for linear regression. Okay. So now remember that the loss function for the gradient descent, sorry, for the linear regression is given by 1 over 2n, summation over I is equal to 1 to n, W0 plus W1 xi, which is basically my model's prediction, minus yi, which is the true target, the whole square, right? So now we need gradient with respect to W0 and gradient with respect to W1. So let's first compute dou L by dou W0. Dou L by dou W0 is given by, you have a 2 which comes to the front, like so x square is 2x, summation over I is equal to 1 to n, W0 plus W1 xi minus yi. So x square has become 2x. These two cancel. Now you go differentiate internally. When you differentiate this internal equation with respect to W0, you get a 1. So that's it. This is the gradient, right? Now, what is dou L with respect to dou W1? It's similar. So you do 2 over 2n. Summation I is equal to 1 to n. W0 plus W1 xi minus yi, right? Now you differentiate the internal one with respect to W1. You get an xi. So xi multiplied by xi. Okay. So now I can use these two gradients to write my gradient descent algorithm for linear regression. So basically repeat until convergence. Okay. W0 is equal to W0 minus alpha times the gradient. The gradient was 1 over n, summation over I is equal to 1 to n, the y hat, which is basically the model's prediction, minus yi, right? So this is exactly what is written here. So this part is y hat, and the second one is yi. Okay. Then W1 is equal to W1 minus alpha times 1 over n, summation over I is equal to 1 to n, y hat of xi given W minus y of I, the whole term multiplied by xi. Is that clear? So in your assignment, you will be implementing this gradient descent algorithm for linear regression. So that is why I said you like all the topics that you need for your assignments will be finished. Like we will finish those things by today's lecture. Okay, so now let's look at like what would happen like if I do this gradient descent for the housing price prediction problem that we had. Okay, sorry about that. Okay, so in this case, you can see that I start with a random W0, W1, okay? And this is the line that it produces. I take the gradient steps one by one. As I take the gradient step, you can actually see that the line is actually getting better and better. Like it gets closer to like what the final solution for linear regression would be. And you can also see that the mean square error is, I think this is, I'm not sure if this is mean square error or I think this is RMSE. So you can see that the RMSE is reducing as we go. Like for example, here it is 238,000, then it becomes 138,000. And now the line is already very close to the optimum, right? And after several steps of this, eventually it converges. So I think now it has converged. So you can see that, well, there is still some, you could still go a few more iterations, but you can see that it has almost converged to 71,423 RMSE, right? So now the line looks as close as possible to the line that you would have got by the analytical solution. Okay. Okay. So now I think, okay, so that is fine.
Yeah, there's a question in the chat.
Yeah.
Yes, the n that is chosen to compute the new parameters W0 and W1 at every iteration, is it the entire data set or just a local
Okay,
region?
so far we are looking at the first version of this algorithm where like n is the total number of data sets. So we will see different versions very soon.
Okay, thank you.
Okay.
We have a question by John.
Yeah.
Yeah, I would like to know for W1, do we use the value of W0 we first estimated, or do we use
Oh, no, so this is normally done simultaneously. So you are updating both W0 and W1 at the same time.
Okay, thanks.
Okay. Okay, so now that is gradient descent for linear regression. Okay, but as I said in the beginning, linear regression is a special example, right? Like, because there's only one minima. So what is the special nature of linear regression loss function, right? In the case of linear regression, the loss function looks something like this, and you can see that there's only one minimum. So it is both the local minima and the global minima, right? Now, this is an example for a convex function. So you will be reading more about convex functions in your next week reading. You could go do it earlier if you want. But one thing that you should know about convex functions is all the convex functions have a unique global minimum. Okay, so right from the beginning of this course, I said linear models have some special property. So what is that property? When you have a linear model with something like a least square objective, right? It produces a quadratic loss function. And quadratic functions are convex functions, and hence like you have a guaranteed single global minimum. Okay. Now, this might not be the case for all the future models that we are going to see in this course. So as we progress, we are going to see more and more nonlinear models. So when you go to nonlinear models, you don't have this nice property of having a single minima. Your loss function would look as complicated as it can be. For example, this could be one loss function. Okay, so in this loss function, as you can see, this is the global minimum, right? This is the minimum that we want to achieve, right? However, there are these two bad minimas or like local minimas. And depending on where you start, your gradient descent is going to get stuck. So for example, if I start here and do gradient descent, the gradient descent will continue, and then it will get stuck here because that is the minimum, closest minimum, right? Similarly, if I start here or if I start here, it's going to continue, and then it gets stuck here. By luck or by chance, if you start here, then the gradient descent will actually go to the true minimum. Okay, so now this is the issue of gradient descent with non-convex loss functions. Okay, so we will discuss more about this in the future lectures. Okay, so now, okay, any questions before I move on? Okay, no questions. Okay, so let's continue. So now there was this question of like, what is n, right? Like, so like, are we going through the entire data set to update the gradients, like to compute the gradients, right? So now that brings us to a second version of this algorithm, which is stochastic gradient descent. When you have a huge data set, let's say millions of data points, that it is going to take you some time to go through all the data points. Okay. Now to do every gradient step, you need to go through the entire data point, like entire set of data points, and then make the first step, right? So now this is a very slow process. Like one way to improve or speed up this process is to use what is known as stochastic gradient descent. Okay, so how does stochastic gradient descent work? So to understand that, let's take the loss function, which can be again decomposed into summation over n different loss functions. N is equal to 1 to n. For every data point, you have a loss function, right? So now we can actually approximate this total loss by just sampling one of these n data points and computing the loss for that, okay? Or in other words, the gradient descent update is going to look something like this. W is equal to W minus alpha times dou by dou W of, instead of having the capital loss, I'm going to have loss just for the kth example, for a random kth example, okay? So now this is going to be faster simply because for every example you can make a step, right? However, this is a stochastic approximation. And most importantly, this is an approximation, right? So which means it's not the exact gradient that we are interested in. So this introduces some noise. Now, when you are in a non-convex setting, this noise could actually help you instead of hurting you. So for example, let's say I start somewhere, let's say I start again here, okay? Now the true gradient, when you go through the entire data set, points you like this, right? Now, since we are sampling only one data point, the noisy gradient might by chance point you like this, and you reach here, suddenly you are in the good region. So now every step is good, might help you to reach this global minimum. So with stochastic gradient descent, even though we start here, there is a chance that we could reach the global minimum. On the other hand, with the full gradient descent, like the regular gradient descent, you cannot reach this place if you're starting from here. Okay. Now, okay, let's go back to our linear regression example. Sorry, let's go back to our linear regression example and do SGD for linear regression. Now, let's say we have n data points. Okay, we are going to repeat until convergence. Okay, now for I is equal to 1 to n. Now we have a for loop over all the examples. Okay, now we are going to update W0 is equal to W0 minus alpha times y hat minus y of I. W1 is equal to W1 minus alpha time y hat minus y of I times xi. Right? So now this for loop, which goes through all the data points one time, step by step, right? So we would often call this as an epoch, okay? An epoch is basically one sweep of all the examples in the training set, okay? A couple of notes. When you do stochastic gradient descent, you should shuffle the order in which you are visiting the examples. Every epoch. If you are visiting all the examples in the same order every epoch, what could happen is there might be a sequence of examples which perfectly cancel each other. So it is going to hinder learning. So in the worst case scenario, you could actually have all the examples canceling each other in a perfect way. So there is like effectively like you're unlearning everything that you're learning, right? So to avoid these complications, like it is better you shuffle your data in the beginning of every epoch. Okay. So now there is also another situation, like, so I mentioned at the beginning that you could use stochastic gradient descent instead of gradient descent when the data is too large and it takes time to compute the full gradient, right? Like there is also another situation where you need to like where you can only use SGD and you cannot use full batch gradient, like full gradient descent. So that is a situation where you have the data coming in stream. Let's say you don't get this fixed data set. The data comes in stream, in a continuous stream. So this is often known as online learning. You have deployed your system. Now it sees new examples. It has to make predictions on the spot. Okay, so now this is like an online learning setting where you could only do SGD. You cannot do full, you cannot wait to collect the entire data to do gradient descent. So you have to do SGD. Okay, now one final note is you could actually get, as we saw, SGD is extremely noisy, right? Like, so we could actually, on the other hand, gradient descent is slow. So we could actually get the best of both gradient descent and SGD by doing what is known as mini batch SGD. So the idea in mini batch SGD is when you have n examples in the data set, okay, you sample k examples where k is much lesser than n. If you have like, I don't know, 100,000 data points, you sample 100 examples. Now this is your mini batch, okay? Now you compute your loss with respect to this mini batch and make an update. Okay, so now this is less noisier than stochastic gradient descent because you have more examples. At the same time, this is much faster than gradient descent because you're doing it in many batches, not with the full batch. Okay, to summarize, when you do gradient descent, you will be going through all the n examples per update. Okay, if you're doing SGD, it's the other extreme. You have one example per update. Okay, and if you do mini batch gradient descent, you will have k examples per update, where k is typically much lesser than n. Okay, okay, so that is gradient descent, and this is one of the central algorithms in machine learning, and we will keep revisiting gradient descent as we learn more and more complex models. Any questions? Okay, well, is it all clear? There are no more questions. Okay, Yamna?
I was just wondering, what's the use of gradient descent? If we're going to use all the examples we have, why don't we just loop through all the data that we have, compute the loss function, and just choose the minimum, the W0, W1 that minimizes that loss?
Okay, okay, so, okay, to rephrase your question, you mean if we can compute all these points, then why do we do, why are we doing gradient descent, right? Is that the question? Okay, she's muted again. Can you raise your hand? Okay, that's the question. Okay, so now this is a toy example, right? Like, so in this case, like I took a 2D example, like where I can actually compute this loss for every data points. And I had only 30 examples to compute these data points, these loss function, right? So for most of the real life problems, like you would have, I don't know, 1 million parameters, and you cannot compute loss for every possible configurations. Remember, W0 and W1 are real values. So they cover the entire real range, right? So this is just for like the toy example. Like you cannot do this like in like real problems. That is when gradient descent is useful. I hope that answers the question. So, okay, so now I want to briefly talk about regularization again. Okay, so let's recap what is regularization. Basically, like regularization means that adding some regularization term to the error function, right? So we looked at L2 regularization, and this is mostly useful in controlling overfitting. Okay, remember, so in the case of, so when you add a regularization, the total error function becomes something like this: ed of w, which is the actual error function, plus lambda times ew of w, okay, where lambda is a regularization coefficient, right? So lambda is a regularization coefficient which controls the importance of the regularization function. Now let's again go to least squares. In this case, my error function, the actual error function, was given by y minus xw transpose y minus xw, right? So now if I want to do L2 regularization, which is what we did before, right? So the error function is given by w transpose w, right? So which is w square. So now the error, the objective that we want to minimize becomes, you minimize y minus xw transpose y minus xw plus lambda times w transpose w. We are minimizing with respect to w, right? Let's just call this equation a star. Okay, so now this is still, like when we discussed about L2 regularization, we did not solve the problem. We just mentioned that this is a quadratic function of w. It has a unique minima, but we did not derive the solution. So now let's actually derive that solution. It's simple. You just differentiate this, set it to 0. When you differentiate the first term, it becomes minus 2 times x transpose y minus xw, plus the second one is w squared, so it's 2w, so 2 lambda w is equal to 0. Okay, now I could rearrange things here. So it becomes x transpose x plus lambda times I w is equal to x transpose y. So all I have done is rearrange things in such a way that the term which doesn't have w goes to the right side. Okay, now w, the solution is given by x transpose x minus lambda times I inverse x transpose y. Okay, now look at this solution. This solution is actually very similar to the linear regression solution, right? So to remind you of the linear regression solution, it was w is equal to x transpose x inverse x transpose y, right? When I add L2 regularization, the only thing that it is adding is this minus lambda. I think it should be plus, sorry. It should be plus in the notes, plus lambda I, right? So, or in other words, this solution adds a positive constant to the diagonal of x transpose x. So now the beauty of this is, like, even if x transpose x is non-singular, even if the x transpose x is not full rank, this, like, and is singular, this particular addition of positive values to the diagonal makes it non-singular. Okay, so basically, even if x transpose x is not full rank, this particular term is non-singular, and hence you can invert it. So this is the point that we touched upon, like in the previous lecture, where I said, oh, okay, so you can do regularization to avoid this problem of not having a full rank matrix, right? Okay, how do we know that lambda I is invertible? As long as lambda is a positive value, you are adding a small positive value to the diagonal, and that makes the whole matrix non-singular. Okay, so now this method of adding regularization, L2 regularization to your least square, right? Like, so this is also known as ridge regression or weight decay in the literature. Okay, so maybe, okay, I think we're running out of time. Maybe I will stop here and discuss more about regularization in the next lecture. So the reason why I introduced this is so that you can start working on your assignments. Your assignments expect you to know ridge regression, but we will discuss more about L2 regularization and also L1 regularization in the next lecture. So before we leave, a quick reminder that we have GatherTown tomorrow. I have already sent you the link for the GatherTown and also the password. It's from 9 to 11. and you need either Chrome or Firefox to access it. So I will see you all during the gather time tomorrow. So it's okay. So let me stop the recording first and then answer some questions.